So, what if every single piece of information, I'm talking everything from a number to a complex image, had its own unique physical address that was literally woven into the fabric of the universe? Well, today we're going to dig into a system that claims it's found exactly that, a universal blueprint for data itself.
It's a massive question, right? But the source material we're looking at today suggests the answer might just be yes, and that the key is hidden in the relationship between prime numbers, geometry, and time. Okay, let's dive right in.
So, where would you even start if you wanted to build a universal blueprint for all information? Well, according to this source, the answer isn't in physics and it's not in computing. It's in the fundamental nature of numbers themselves. Okay, I know, that is a mouthful, but let's break it down, because the core idea is pretty fascinating. What it's basically saying is that prime numbers, the fundamental building blocks of math, they aren't as random as we think. This system claims there's a hidden, predictable pattern to how they're all organized, and the secret to unlocking it is a surprisingly simple thing called digital root recursion. Think of it like finding a number's core identity. You're just boiling it down to its single-digit essence. So, like the example here, the number 73 becomes 1. This isn't just a math party trick. This process of simplification is actually the very first step in translating these abstract numbers into a physical, predictable structure. Now, you might be thinking that our base 10 number system, counting in tens, is just a human thing, because we have 10 fingers. But this theory argues it actually has a deep physical meaning. The source claims that base 10 is the exact point where physical measurements of time and distance start to go their separate ways in a specific experiment. This is super important because it tries to ground this entire system in observable physics, not just abstract math. So if there's a universal blueprint out there, how do we actually access it? Well, the system proposes a key, and it's something called the Dimensional Retrieval Card, or DRC for short. The best way to think about a DRC is like a cosmic zip code for a piece of data. But it's not just pointing to where the data is. It's a full-on coordinate that describes the data's location in this multi-dimensional space defined by things like shape and phase and even color. So let's unpack what a DRC really does. First, it's a passport. It gives every little bit of data a unique, verifiable identity. Second, it's a time node, which means it locks that data to a specific moment in a sequence, creating a history. And maybe most importantly, it's a retrieval cipher. It's the key that lets you perfectly and predictably rebuild the original information. So it's not just storing data, it's giving it an identity, a history, and a key. Now, this all sounds really abstract, I get it. So how does the system actually build something tangible from just a string of numbers? Well, the whole process follows a really clear, predictable chain. Here's the chain of logic. It all starts really simply, by counting the prime numbers inside a small set of numbers. That prime count isn't just a number, though. It becomes what the system calls a time step. And here is where it gets really cool. Each time step is intrinsically linked to a specific geometric shape. It's like a predictable cascade, where one step just logically and unavoidably leads to the next. And this is what that translation actually looks like in practice. A prime count of 1 always gives you a circle. 2 primes always creates a triangle. 3 gives you a sphere. 4, a square. The big takeaway here is that there's zero ambiguity. It's a direct, hard-coded link between a number and a shape. The math itself literally dictates the geometry. This powerful theory isn't just an idea on paper. It's actually been implemented in a software system called AxiomARC, which puts all these principles into practice. And yeah, this isn't just a concept. What you're seeing is a little snippet of the actual source code. The theory has been turned into a real, functioning software system built to generate, manage, and use these dimensional retrieval cards. Inside the system, a DRC can exist in 3 different states. Most of them are latent, which basically means they're in storage, waiting to be used. A small number are active, they're currently processing information, and in a way, they're kind of wearing down or gaining entropy. The rest are transitional, moving between those 2 states. So you can see it's a living, dynamic system. Okay, so the theory is elegant and the system is built. But the big question is, does it actually work? Let's take a look at the results. So here we can see the system being given a really tough challenge, handling the famously complex Mandelbrot set. This is our before picture, the data that's being fed into the AxiomARC protocol. And here is the after. The system takes the DRC it created and reconstructs the original image.
The result is measured by something called a structural similarity score, or SSIM. Now, a perfect score is 1. As you can see, the reconstruction here scores 0.9997. That means it's not just close, it's a near perfect, almost pixel-for-pixel match.
Let's just pause on that number for a second. 99.97% structural similarity. I mean, that is an incredibly high level of accuracy. It really suggests that the retrieval cipher part of the DRC works exactly as claimed.
And this wasn't some one-off fluke. The system's performance is constantly being monitored through dashboards just like this one. They track something called a coherence score, which is basically a live measure of the system's overall health and stability. This tells us that the high-fidelity reconstruction is repeatable and stable over time.
So, what does all of this mean? If this system really works the way it's described, it represents a fundamentally new way to think about information storage and retrieval.
This brings us to a really powerful summary from the source. A DRC is an entropy-aware system. Remember those active and latent states? It's actively managing the life cycle of data. And it's a temporal memory ledger, because it's not just data, it's data locked to a specific time step. When you put it all together, this isn't just a new way to store files, it's a complete reimagining of what memory itself can be.
And that leaves us with this final, kind of mind-bending question. If every piece of data can be given a unique coordinate that's based on the fundamental laws of math and physics, what does that change about our relationship with information itself? What becomes possible?